So I will be posting my PowerPoint online. My PowerPoint online here has a lot of animations. They worked great for an old version of PowerPoint, but what I'm finding is that newer versions of PowerPoint have trouble running all the animations I've put on this. This is a very visual chapter, so might as well just see it run on my computer, I would say, just in case you can't run it on your own. Google Sheets definitely won't run it, so don't even try that. What I want to focus on here is the idea of a continuous wave. So if we generate a continuous wave, it's a disturbance that keeps going up, down, up, down, up, down in set fashion. If I want to up the frequency, it's going to look like this. You can see that this oscillation is happening more rapidly. And right now it's set to 3 Hertz. Basically what that means is that we go up and down 3 times each second. In fact, that's what those green dots you see are doing as well. They go up and down 3 times each second. If I lower the frequency to something like, we'll do like 0.5 Hertz, all of the sudden you see a different shape to the wave. And one of the things that is interesting here is that you're going to find that the wave speed is unaffected here, and you can prove that to yourself by using this timer app. A little bit harder to see the wave here because it's harder to see the crest. Maybe if you did it like this in slow motion, you can clearly say, all right, how long does it take for this crest to get from here to here? It doesn't matter what the frequency is. It's going to take the same amount of time each time, but what ends up happening is you get more and more up and down oscillations in that time period as well. But you take a look at the continuous wave, it looks like a sine wave. So this is where there's an animation in my PowerPoint, which I think is a pretty good one, because here you see our continuous wave. It's moving to the right, and that red particle there, that's one part of the medium. And what it does is it goes up and down and up and down. Now we got 2 graphs that are generated here. This graph right here, what it does, it keeps track of where the red dot is as a function of time. Is it up, is it down, and how far up and how far down? And so that you see, as it starts to go up and down, it's keeping track of that. But then, picture this. We can take a picture of this continuous wave, let's say with a camera, and put our ruler up to it. And we get 2 different data sets by doing that. We get the amplitude versus time data set, and you get the amplitude versus position data set. Think of this one as a snapshot in time. This is a picture. Whereas this one is a recording of the single point on the medium. Now both graphs look very sinusoidal. All right, so what we want to do is talk about what kind of information is in there. So looking at our continuous waves, you saw a few things here. You saw that I can change the frequency of the wave. And what we had here was your wave could look like this, or your wave could look like this. This is what we would call high frequencies. And what you saw is that the up and down oscillation had to be a lot more rapid to generate that than it did this. This would be a low frequency. So relatively speaking, we can compare our 2 waves here. This one has a higher frequency of that one. That means there are more oscillations up and down per second. Right now, what we did in that animation was we generated an amplitude versus time graph, and you generate an amplitude versus position graph. We'll just write X for position here. And they both look sinusoidal, so a lot of people go, ah, they're the same thing. But they're totally different units. This is in seconds, and this is in meters. All right, so they're totally different things. What we want to focus on here is that we can get information out of these graphs, and you're going to see on that sheet that I have you hand in, that we give you graphs and you're expected to look at the graph and be able to pull out a certain amount of information here. But it matters what graph are you looking at. Are you looking at a graph where the horizontal axis is time, or is it position? Because if it's giving you time, it's conveying different information than if you get position here. But what you want to do is you want to look at here. You get a full oscillation going from here to here. You go up, down, and back up again, so you end up exactly where you started. This time gap between here, that is what we would call one period. One full oscillation, that's how long it takes, is that amount of time from there to there. So that's capital T, that's the symbol for our period, and that's measured in seconds. We know that frequency is related to the period. We said that frequency is always 1 over the period. So if you want your frequency in hertz, there it is. Remember, your period is always in seconds, so your frequency will be in hertz, and then you can get the frequency of the wave by that graphical interpretation there. Now, if we go over to this graph here, you may be given a graph of amplitude versus position. If you are, we still want to go crest to crest, but now this is a completely different measurement. This is a measurement in meters, and it's actually something we call, it's a Greek letter, lambda. That's the symbol for wavelength. This is wavelength here, and wavelength, basically what it means, it's the distance traveled. Look, I'm running out of room here. In one full cycle. So it takes a certain amount of time to go through one full cycle here. And our wave travels to the right, and it travels a certain amount of distance. You can get that distance simply by taking your snapshot. That's what this one is. This is a snapshot. You can literally take a picture with the camera and hold the ruler up to the picture and then get your wave parameters here. This snapshot in time gives you your wavelength, and what we want to do is just take a look at that distance. And when you go from crest to crest, you can even go from trough to trough if you want to. That's going to get your wavelength. These two things are always related to each other, because if you look here, this thing has a long wavelength, whereas this thing, relatively speaking, this has a short wavelength. So you're going to see that frequency and wavelength kind of play off each other. If you have a high frequency, you're going to have a short wavelength, relatively speaking. If you have a low frequency, you're going to have a long wavelength. And then the relationship actually gives you wave speed. How fast is the wave traveling? Wave speed, velocity. What would make sense is lambda over t. Here's why. The amount of distance you travel is lambda. The amount of time that has elapsed is t. So that would get you your speed in meters per second. But since period is related to frequency, a lot more convenient often could be just taking frequency, multiplying it by wavelength, since you see 1 over t here. So this is like the golden formula that applies to all waves. If you know the frequency and you know the wavelength of the wave, then you can get its velocity. But conversely speaking, if you know the velocity and wavelength, you can get the frequency. If you know the wavelength, if you know the frequency and the velocity, then you can get the wavelength. If you have 2 out of 3, you get the third. And I would say that in those problems, you're presented with graphical data. You have to look at, see, what's it in? Is it in seconds? Is it in meters? Because you got to know what type of information you're going to pull out of it. Maybe you pull the period out of it. Maybe you pull the wavelength out of it, and you should be able to fill in those charts or those tables no problem, because you gradually get all the information that you need. They may also give you the velocity in those problems as well, so keep your eye on those.